So these are error bounds for midpoint and trapezoidal. And so these are just formulas that tell us that our error that we calculate will be less than this number. That's all it is. It's a bound that if we have some number of n subintervals from b to a of our function, then the error that we calculate will be less than this. And that's why we put the absolute value. So whether it's above, which is negative, or below, which is positive, we're going to have something that's less than this number. And why is the second derivative used? Well, you got to think about it. With these two, we're drawing lines. And so if something is more concave, right? Bigger second derivative means the rate of change of your slope is quicker. You get something that's more concave. So when you draw the line between it, you're getting a lot more error. And so you have something that's not very concave, right? You have a lot less error. So f double prime of x right here is small. F double prime of x here is large. So large double prime, more area, more error. Small double prime, less error. Makes sense, right? All right, so we need to find out what they are. So we have an a. A here is 0, b is 1, and is 8. Our function is cosine of x squared. Remember, the f of x is whatever's inside. Now we have to do the derivative. So we get negative sine of x squared times 2x, which is negative 2x sine x squared. Now that we have two variables, we need to do product rule. So negative 2, and then cosine x squared times 2x, and then we do our little cross multiply. So negative 2 sine x squared, and then that would now give us a negative 2x, and positive 2x is negative 4x squared cosine x squared. So we end up with negative 2 sine x squared minus 4x squared cosine x squared. All right, so now we're going to plug it in the formula. But what we need to do first is find out what our absolute value of f of x is. So if you look at this, we have e to the t, and we're going to plug everything in but the f of x, f prime double x. We're going to leave it the way it is, the second derivative. And then we're going to get b minus a, so 1 minus 0 cubed, over 12 times 8 squared. So what we want to do is put a little less than or equal here and find some upper bound for our f double prime of x, something bigger than the absolute value here. So what value would this be? And so we can just go back here and look at each of these individually. So we're going from 0 to 1 for our x. So that means our absolute value of f double prime of x, right, is equal to, and we can now just change it. We're going to put the absolute value on there. And I'm going to get rid of both negatives. If you're going to get rid of one, you got to get rid of all of them. So 2 sine x squared plus 4x squared cosine of x squared. And then we just look at it. Well, inside we know sine's biggest number is 1. Cosine's biggest number is 1. And for x squared, as you go from 0 to 1, so remember our x here is between 0 and 1. These are the numbers we can plug in, right? So as we go from here to here, then we know that this is going to be less than or equal to 2, of course. And then sine would be 1. This would be 1. This would be 1. And then for x, as you plug numbers in here, fractions are going to get smaller and smaller until you hit 1. So 1 will be the biggest as well for this, and 4, and 2. So if you add all those up, right, we end up with 2 plus 4, which is 6. So we know that this is less than 6. Mandatory, no matter what, this cannot get bigger than 6 on the interval from 0 to 1. So we can say that this has to be less than 6 for that one. And then it's 1 minus 0 cubed over 12 times 8 squared. And then if we calculate that, we get 1 over 128, or 0.00078125. So 0.078. Now, there's a much more modern way of doing this. And if you think about this second derivative, we can just plug it in the calculator from 0 to 1 and actually calculate and find what is the biggest value. So let's do that instead. So if you input that second derivative exactly how it looks, remember we're looking for positive or negatives, it doesn't matter. And we go in here and we go from 0 to 1. You can even change our scalar back, it doesn't really matter. But now we go zoom fit, and what it will do is find the largest and smallest values for us. So there is the biggest and there is the smallest, but we are looking for absolute value. So if you go back to your window, it tells you what those are. That smallest one, which is down here, was negative 3.8448. So we could just say that that would just be 4. Remember, positive 4. And the other one that we get here for y max is 0. So if you look at our graph here, right, that would be 0. So if we hit trace 0, you get 0. All right, so we can actually just say 4 instead, and it gives us a little bit better calculation. So we could say less than or equal to 4, and that's just 1, 12, 8 squared, and get something that's even better, which is 0.0052. 00, I forgot a 0 on that one too. 0052. All right, so it's a better estimate than this one. So we have calculators nowadays. You can just plug it in, or you can graph it by hand if you want. But yeah, plug it in your calculator by doing window, set your interval, hit zoom fit. It graphs it for you. You go back to your window and you can actually see what the y max and y min are and pick the one that is the biggest absolute value, whichever one that would be. Set that equal to it. It'll give you a better estimate. All right, now let's do it for midpoint. Well, it's the same second derivative. The only thing that's changing now is at 12 and 24. Remember when we did the errors from the beginning, the actual calculating the actual error, not the bounds, but we saw that the midpoint was actually half as small. Remember? It was a factor of 2 going back from midpoint to trapezoidal. This was a better estimate. So now all we have to do is take this one and divide it by 2. So if we take the error of the midpoint, we just have to say that it would be less than or equal to, and then we would do the same thing, 6, 1 minus 0 cubed over 24 times 8 squared. But basically all we're going to do is divide it by 2. So we're going to do both together. So if we take this one and divide it by 2, we get 0.0039. So 0.0039. And if we take the other one and divide it by 2, you should already know what that one is, but we're going to do it just because 0.026. So if you're using the calculator, that's what you're doing. If you're doing this by hand, that's what you would get. So it's just a factor of 2. That's all it is between this. So if you wanted to make sure that you found an error bound for both, right, then you would just pick the trapezoidal. So the trapezoidal would actually cover both of them as an error bound, because this one's always going to be twice as big as that one. So you can just pick that one as the major error bound for both, because you're going to get so that would just be less than 0.0078 or 0.0052. Okay, one quick little fix here. That should have been 0.0026. And it should be smaller because this is our calculator, which is giving us a better estimate than this one would be. So it's giving us a smaller number than we would have had here, giving us a smaller error as well. So it should be 0.0026.